Maria Zurek. She is a postdoctoral researcher at the Lawrence Berkeley National Laboratory, and Maria is conducting research on what keeps the world together, so rather big research. And Maria, the stage is yours.
Perfect. Thank you so much. Okay, let's start. Let's start from the very beginning. 14 billion years ago, our universe was born in the Big Bang. But what happened in the very first seconds, just after it, determined the structure of matter we are all made of. In the beginning, the universe was hot, dense, and filled only with the most fundamental building blocks of matter called elementary particles. Then, while extending and cooling, the atoms were created. In the center of the simplest hydrogen atom, we can find the tiny proton. And I ask, is it the most fundamental particle? What actually is the proton? Well, to be completely honest with you, the proton, it's a mess. It's a complete mess with a complicated internal structure. While the hydrogen atom could be compared to a beautiful, well-organized ballet dance where the electron is dancing elegantly around the proton itself would be a rock concert full of drunk, sweaty people bumping into each other. Proton is full of, as far as we know, elementary particles called quarks and antiquarks and gluons binding everything together. You've maybe heard, well, proton is made out of 3 quarks. You know, proton is made out of 3 main quarks and zillions of quark and antiquark pairs popping up and disappearing, and zillions of gluons inside. In my experiment called STAR, together with my colleagues, we reproduce conditions few seconds just after the Big Bang to look inside the proton. We smash protons accelerated almost to the speed of light and study the debris of these collisions in huge particle detectors to ultimately probe the direct interaction between the basic constituents of the proton. The more energetic the collisions are, the messier structure of the proton we can see and better resolution we have. In my analysis, I try to understand how the spin of the proton originates from its messy mosh pit structure. Protons behave like spinning tops, but unlike the spin of a toy or a ballerina, the spin of the proton is an internal quantum phenomenon. Spin is a basic property of every particle like mass or charge, and is related to its magnetic properties. When particles with spin travel through a magnetic field, they will behave like small quantum magnets. But in a broader sense, spin is an essential property which orders the electrons and nuclei in atoms and molecules and determine the stability of matter which we and our whole tangible world is made of. Spin of the proton is exactly 1/2. It can be oriented up or down. For years, scientists thought that the spin of the proton originates from the spins of its 3 net quarks, with 2 spins up and 1 down. But, surprise, experiments showed that spins of the quarks can contribute only to, at most, about 1/4 of the overall proton spin. The rest has to originate from gluon spins and messy mosh pit quark and gluon internal motion. To understand how gluons contribute to the overall proton spin, I study very special type of proton-proton collisions where the spins of the colliding protons are oriented in the particular way, like this, or with 1 spin flipped. I searched for jets, showers of particles in the debris from these collisions, which suggest and tell me, yeah, these were mostly gluons which interacted in this reaction. I measured the difference of the numbers of jets of particles produced from one configuration of the proton spins, colliding proton spins, and the other configuration. And from this, together with my theory colleagues, we can understand how gluons are aligned inside the proton and how their spins contribute to the overall proton spin. So, what have we learned? Well, with the current experimental resolution which we have, we can access only gluons that carry more than about 5% of overall proton's momentum. And they contribute to about 40% to the overall proton spin. It's a lot, and is a crucial step in understanding the fundamental structure of matter which builds me, you, and our whole world. But as physicists, it just tickled our curiosity. We are building an even more precise experiment called electron-ion collider to look even deeper into the proton, to access more gluons, understand the proton spin, and actually get closer to answering the question, why does the universe exist as it is? Thank you very much.